Okay, so let me go to Mark.
Tim, I would like to add to that. I think we're going to have a presentation from him later as well, because what we're trying to do here is figure out. So you got this version of Alzofon, this theory about why it would work on the ground at the front line when people are actually trying it. What do you want to see in the experiment? So Tim, if you could start sharing all of the screens.
Okay, so yeah, and this is the part. This is the part I have to figure out. It's been a while since I did that. So if I remember right,
Spotlight the FS CAD COM. That's Falcon Space CAD computer, and we're just sharing Fusion 360, so we'll be able to.
What about Falcon Labs?
So that's inside the Faraday cage. So get that one as well. So you want to
spotlight that one, and then FS, yeah. Add spotlight. Okay, that's 2 cameras that I have.
Okay, perfect. So on the left, you guys can see the inside of the Faraday cage. And on the right is the part that's actually been removed from the Faraday cage. We're working on it right now. That's where the main experiment is happening. On the other side of the wall, I'm going to change screen here for a second. Okay, there we go. Now, the other side of the lab over here, we have these logimetric units that we got from Sandia Labs, giving us a full range from 400 megahertz up to 12 gigahertz at least 200 watts. So this one is the X-band unit, and it has a waveguide output over here. The waveguide travels through the wall over there, through that opening, into the Faraday cage where we're actually running the experiment. Now we got lots of cameras here. Okay. And now we're back inside the Faraday cage. The waveguide is coming in from the side. And going in between the plates of the electromagnet. I'm actually inside the Faraday cage right now. So it's pushed out a bit because we removed the centerpiece a little earlier. For those who don't know, the main components of this experiment are homogeneous magnetic field, along with a with an RF frequency pinging the sample at its Larmor precessional rate of 28.025 gigahertz per Tesla. That's another question that I have for Lucian and for anyone else. If there's any other valence bands of electrons that we can, ring it at, then we should try those ratios as well. I couldn't find much information about that online. So you can see the models moving now. That's me with the magic mouse. So in green over there, we have an isolator. That's the first component that's coming out of the the power end. Then there's a cross guide, which basically gives us the forward and aft power. That there's 2 wires that connect to each one of those tubular shapes, and gives us a reading of how much cross power is entering that secondary chamber, and that's how we know, what's going in, what's out. It's basically our SWR meter for ham radio guys. The next piece is just the blue one. That's just an extension, so everything fits. And then here is the waveguide, or the test chamber itself. As you can see, there are already holes drilled into it. There's more holes than that right now. We're actually figuring out how to process lots of bits of information of what's happening inside that chamber. So as it stands right now, we have the capability to pump about 200 watts at least into this little chamber, and we have almost perfect homogeneity over the field. It's not part of the 3D model over here, but there are magnetic lenses between those the magnet plates and the chamber. These, I guess they look like the base of the ARV. Those 2 pieces, those are the representation of the electromagnet in this process. So the sample sits in the center over there, and it's riding on a rail going up and down two strings that are on either end of it. It's held in place with two rubber bands, trying to keep it as simple as possible. I'm going to share my video for my cell phone. Tim, can you turn on the video for a second? Bring that in. Okay, there we go. So basically, this is the rail system that we're working with right now. A sample will sit in here. Here's another one. Sample sits in between these rubber bands. There's holes on the plastic, and that slides up and down. This is the test chamber as it stands right now. Actual physical unit. So this top was made out of a solid piece and machined that kind of angle. We have a viewing camera. This is a fiber scope. It's basically an analog way of getting an image down a pipe. So there's really no electrical parts in there, and I might be able to get you a view inside of it. Yeah, basically, we got to hook that up to a camera properly, but that allows us to see inside the chamber. There's also a light that's added onto it, and it moves. So that's going to give us a view inside the chamber. We're looking at concepts to get a thermal image, or at least a thermal probe coming into the chamber. And there's a couple ways to do that. We got some germanium windows that we might stick on the bottom or on the side. It's a pretty complex process. We have some parts coming in. We'll figure out if it's even possible. So the result of the first test was we heated up the sample to the point that the original rail melted. And you can see that over here. We knew that it was melting because we saw smoke coming out of the waveguide. So yeah, there's that. It didn't take very long. We've never had this much power actually run into the chamber before. But the fact that that was the only thing that warmed up is very heartening, and shows that we're doing something right. This is the scale measurement. It's being held by a fishing line, basically. I think this is a multi-thread fishing line, and that goes up to either a mechanical or a digital scale. And that's another thing we're going to get into in a little bit. Okay, so here's the rest of the actual physical unit. There's also a twist at the end of it, just because of the way the waveguides are oriented. Here's the isolator, the cross guide, and the extension. This is that scope we were looking at before, the fiber scope. As for equipment over here, we got the Logimetrics 200-watt amplifier. It's starting off with this signal generator. For power supply down here, the KEPCO. This is feeding power to the electromagnet. On the end of it, oh, sorry about that. On the end of it, we have a so the KEPCO power supply is what's powering the electromagnet. There is a shunt in the back over here. You can't really see it very well. And the readings off that shunt are going to a vernier scope, which gives us live data on the lab computer over here. So the data we're able to get from the Faraday cage is, we're going to try to get a visual inside of the chamber. We're going to try to get temperature inside the chamber. Those are kind of difficult to achieve. We definitely have two load sensors and two GoPro cameras that can be in there, and they're Faraday shielded, so there won't be any damage. We're also looking at getting RF loads for the edge of for inside the Faraday cage, so that anything that does escape the test chamber will get attenuated pretty quickly, so as not to damage the rest of the equipment. And as for samples, so we got lots of samples, and I'm just going to set up over here on the computer. There's another I can share screen from here. Hold on one second. And I'm sorry, I do apologize for before. We were having computers shut off on us. It was not fun. Okay. How do I do this? No, this one needs to share screen. Okay. Do you see that? Tim, I can't hear you.
Yes, I see a spreadsheet.
Oh, okay. So these are the samples that we have made out of epoxy mixes. This was when Jeremiah was down here about a year ago. Some of the samples have aluminum metallics, and there's other oxides as well. As you can see, the first one that we ran was sample number 2, which is powdered aluminum with or 3.5 grams of powdered aluminum, 0.3 grams of iron powder, and then there was the structural epoxy. It looks sort of like a little puck. It weighed 5.7 grams. So that test was kind of inconclusive. It did heat up, and the scale bottomed out, but that was because the test measurement or the rail system that we had it on was just melted, or maybe it became weightless first. I have no idea. There's no way to know with with scale, with the sample holder melting, which is why we're trying to get the camera in there using the fiber optic system. But these are the samples that we have right now set. We also have osmium. There's these little osmium spheres that weigh about 1 ounce each. All of these powdered metals that you see over here, they're also, we have more of it available. So if you think of a different combination that can provide different effects, that'll be interesting. We also have bismuth discs that we machined out. They weigh about 20 grams, I believe, because bismuth is pretty dense, almost as dense as lead. And you name it, there's a lot of different sample materials here. We can use glass, but if there's any sample anyone would like to see ran through this experiment, now is the time to call it out and give us your reason. If you want to see anything different in the test chamber or the execution, now's the time to talk up about that as well. And I guess we can go from here and just see what people want to see. Tim, are you there?
Yes, I am here. Sorry, I'm spacing out a little bit. It's that time of the day, man. I need some more coffee. So we do need to have our discussion thing. You wanted to seek open input for different experiments, right? Oh, Mark, you just dropped your voice.
Oh, I'm sorry. For different variations of this experiment. That's
yeah.
really
So let's open things up. Let's open things up. So anybody, let me see, allow participants to unmute themselves. That is enabled. So if you guys have suggestions, ideas, anything like that, go ahead, unmute yourself, speak up.
I would have a general comment or question. So we have these various materials. Is there a way to see the actual structure at the level of, say, how the metal is this? Well, what's the crystalline structure? What's the distribution of the various components? For example, bismuth trioxide. Again, think that the bismuth is a collection of neutrons, protons, and so on. Three oxide form another structure. So if we think that there are some various Platonic solids for each neutron and proton, then maybe we start to understand how the corresponding fractional charges are interact with each other. I mean, it's a solid state physics problem here. To understand better the materials at the level of their, say, molecular structure, but from the point of view of Platonic symmetry.
Okay, so what does that mean in actuality? Which sample are we looking for, and how is that going to work?
That's a tough question because I'm not a physicist. But again, the idea is a neutron. Think that neutron and protons have a cubical, like cubes, with the three axes representing a flow of positive and negative electric field. Are you with me so far?
Not really. I'm kind of looking for more like straight up suggestions of what to try. Well, there's also magnesium. We have tin, actual tin foil, different types of irons. Should we try variations of the magnetic field? Should we try pulsing the magnetic field?
Okay.
We're talking hardware, not theory. So we need to get to the hardware. Send me the link on eBay of the part of the sample you want to get tested, and we'll do it.
That's like a random choice. I mean, it's from the name. It's impossible to say if it's a good material or not. I also read from the text from the book by Frederick Alzofon, actually by his son, Gravity Control with Present Technology. I think you've heard about it, right?
Yes, I have quite a few copies of it.
And chapter 21 starts explaining his experiments, but he has only one material, aluminum. Doped with some impurities. I don't recall exactly how and what.
How exactly was it formed? How was it doped with impurities? I think he might have been doing this. I have a sample. So this is 5-9 aluminum slugs, and they said that he put a little bit of iron on it. So he might have been using, I don't know if you can see my video here, but we have a little bit of ferrofluids. Maybe if I dunk some of, one of these pieces of 5-9 aluminum in the ferrofluid, that would be an equivalent resemblance of what Frederick was trying to do.
I guess so, yes.
Well, but there's another possibility is that he was actually mixing aluminum powder with the iron powder inside an epoxy, which is another rumor I've heard. So you have that. The other option is a sheet of aluminum with a little bit of ferrofluid on it, which actually gave me 17.8% weight loss in a previous experiment. So
much?
But there was a lot of noise in that. Here, I think this was the sample. No, this was not.
Mark, what is the expected performance that you are expecting from each experiment? And what kind of output in the end?
That's a great question. I mean, there's different theories, relating to what would cause the effect. Todd, if he's there, he's mentioned that having a gradient in the field might help. So I don't know. I mean, if the experiment works
Right,
properly,
force is gradient, the gradient of mu dot B. And mu is the magnetic moment from the spinning electrons. And B is your magnetic field applied. So the force that you get is the gradient of mu dot B, not just applying the magnetic field.
okay, so what type of gradient are we talking about?
The directional gradient. I mean, you've got a magnetic field, and you're multiplying by the magnetic moment of your electrons. That gives you a potential energy. And then in order to get a thrust out of it, you need to take a directional derivative. So whichever way, you take the derivative in all three directions, and whichever way is least, that's
What
the way
type
it's
of,
gonna move.
what percentage are we talking about? 3,000 to 300 Gauss, or 3,000 to 3,300 Gauss? What order of magnitude is this gradient?
In your case with 28, 9 gigahertz electrons,
Yeah,
it doesn't-
we're at
it doesn't have to be
Larmor is
much.
around Larmor is around 3,300
3,300 what?
Gauss.
Okay. I'll send you a calculation of how much of a gradient, but it would be just as easy to just test it and then see what the gradient is. What the actual
No, you'd
gradient.
actually have to engineer something like that using an iron lens. So we got a number for the gradient variation that we can, would it be 3,000?
I can calculate, it's easy. So I can't do it in my head, but I'll get it to you.
Okay. Okay, so yeah, get me that number. We can work on that variation of it. Does anyone else have any comments on the equipment or the setup?
Hi, thanks for opening this up to open discussion. I'm sorry, I feel like I missed out though on just the basic statement. Can you kind of just briefly restate the overview of what's all happening, please?
We're going over an experimental setup that we have for the Alzofon experiment, and I think I gave a pretty thorough description of what it is we're doing, and we're for some reason we have this computer. I can stop this share, but we were looking at the experiment from several different angles and seeing what variations we can do to it moving forward.
Thanks so much. I'm sorry if I missed something. I understand you're running materials through a process
You
and
mentioned
detecting a weight loss.
Mark, I'm not sure who was asking that. Are you able to speak to that?
I'm trying to stop the share on this
There we
computer.
go.
Oh, okay, there we go. Yeah, the share was.
Do you want me to take your camera off? Here,
Yeah, I just took that off as well.
remove
It's a little confusing
spotlight.
because we have.
So we've
we have
got
so many
Falcon
things
Labs and FS CAD. We've got those two up. They're going still.
Okay. Oh, okay, there we go. Now it's inside the Faraday cage. So, yeah, what was the question again?
I think he was asking how much weight loss you've measured.
Oh, okay. It also cut out because of the internet over here. We've seen so far 17.8% weight loss on an aluminum sample. There was lots of noise in the scale, which is something we're worried about with this setup as well. It was at much lower power as well. And that was using a solid aluminum sample. Probably, it was like sheet metal thickness. Total sample weight was about 2 grams. It wasn't taking that many notes back then. So we're really trying to replicate this experiment properly with, and document it as well as possible, looking at it from many different angles.
Yes, if I may, Mark, how much was the noise from the 17% you were talking about?
I posted the video on YouTube. It's about a 30-second video showing the part where most of the weight loss happens. The entire video is about 3 hours long, where I'm tinkering with knobs. I'd prefer that you watch that and see for yourself. Like it really needs lots of analysis to figure out what we were actually seeing over there. While you're at it, you could also check out Jeremy Reese's The Alien Scientist YouTube channel. We did an experiment right after the SETI talk that may have had positive results. You can check that over as well. That was with rotating magnets, similar to what Todd Desiato was working on earlier, but it also combined high voltage with the rotating magnets. And I think we may have seen a couple grams of weight gain in that setup. But yeah, the information is out there. Getting it concise in one place is a job that we need to work on.
With rotating magnets, the analysis is a little bit more difficult, I would say. But I would stick with the Alzofon's approach. Microwaves, trying to find the resonance frequency, the EPR, right?
Yep, the EPR.
And see how the sample responds to the corresponding treatment.
Right, but what kind of sample would we put in there based on your theory, and why?
To me, I think it's what Alzofon used still has a lot of potential to be more consistent and do more experiments with variation. Frequency used, the gaps, maybe temperature, and then of course once you understand well what happens with one material, then you start like Edison to use hundreds of materials and see which one seems to respond better to such dynamic nuclear orientation with microwaves.
Okay. Does the microwaves need to be in any special order, pulsed, continuous, circulating,
yes.
traveling,
So,
standing?
That's interesting. That it's like putting in motion a swing. So you have to pulse it very carefully, not to come across. To diminish the amplitude instead of increasing it. So it's like pushing a swing.
Decreasing the what?
The amplitude of the rotations of the electronic spins.
Oh, to be increasing the amplitude. Is that what you said?
And also, again, we have a lot of information from Alzofon's experiments. And in
there's lots of contradictions in there as well. It's not very clear what the sample was.
Yes, but the type of microwave, for instance, on page 141, experiment number 1, you see that the pulses are 8 milliseconds wide. Then they're turned off 8 milliseconds. There are some other like 6 milliseconds pulses. And I don't know if you know that he took this from the measurements of an Air Force airplane
Mhm.
with the measurement apparatus chasing an UFO. So one would may conjecture that probably the UFO knew what it was doing and had the right parameters, but we don't know what material he was using, maybe at its core, or what material was built of, which reacted at the corresponding microwaves and pulses and gaps and so on.
Okay, so you're talking about the frequency of the pulses at 8 milliseconds. Was there any other information, or is there any other thing, any other changes that you can think of based off of your take on Alzofon's theory? Anything engineerable? Does this layout need to change because in any way? Does the pulse time need to change? Does the I don't know how many variations to the field you want to include, but there's always going to be something, you know, somebody saying that, oh, you didn't try this. So we want to make sure to cover all of our all of our bases first.
So each material has a certain relaxation time. So you have to allow gaps corresponding to that relaxation time.
Okay, and where do we get that relaxation time chart from?
Now that I don't know. So it has to do with I mean, some solid state physics textbook or physicist specialized in EPR or even MRI, because this is very similar to MRI.
Yeah, I've been asking around for such a chart, and if anyone has or knows of such a chart that shows you the dynamic nuclear orientation relaxation times of different materials, please send that to us at falconspaceprogram@gmail.com, or you can just respond to the email invite to the conference with that documentation. But I have been asking around, even the head of the University of Albany's physics department. I think I asked him for that as well, and he wasn't sure where to find it. So it seems like there's some information cover up relating to dynamic nuclear orientation, which only gets me more excited to work on it. But these are the things that we know that we don't know about this experiment. Another thing that we know that we don't know is the if there is any other gyromagnetic ratios that we might hit, like for different valence bands of different materials, of different metals, and even non-metals, even dielectrics. Todd Desiato mentioned before that we in another meeting that we should try distilled water. Some people have recommended using plastic. Well, if dynamic nuclear orientation is using valence electrons to get into the core, it should work at any, with any material that has valence electrons, to some extent. So yeah, it should work on a range of materials, and for different reasons on different materials. I just don't. That's the information that I know that I don't know. And we're going to run through all the samples that we do have, and if anyone has any recommendations for other samples to try, you can hit us up and or come down and help out with the experiment. With some of these samples, one thing's for sure: if it doesn't create weight loss, we'll vaporize it till it weighs nothing. But that won't be positive results. Jeremy,
No,
is there
Mark,
anything?
we
Yeah, go ahead.
we need to make sure that we don't vaporize our occupants for whatever spacecraft we build. That would be a very negative side effect.
It would be, and if you look at the Rendlesham Forest case, and actually many other UFO cases, if you get really close to these things while they're powered up, you are going to get vaporized or like burnt. So,
Cash Landrum.
yeah, there's a lot of cases. What's his name? The redhead dude, Fire in the Sky. Yeah, he got hurt
Travis
by
Walton.
Travis Walton, exactly. Good old Travis. Yeah, he got some sort of radiation burn. So whatever we're expecting to create these effects probably has some radiation associated with it, which is why we have the Faraday cage.
So let's
that,
talk about dimensions of the sample. Like how what's the maximum size of this thing? It's not the size of a hockey puck. These are a little smaller than that. The samples that you showed me that we were working with before. I just want to put a challenge out there to people in the audience. If anyone has access to like metamaterials or thin films or any of these other, production graphene coatings or anything like that, so to make us some samples, what size we need, and maybe some people can use their advanced manufacturing capabilities to make us some more advanced types of samples, so that we can help narrow down our search.
Oh yes, I love that idea. Tim, can you spotlight my camera on the phone right now? This is actually the sample holder.
Yeah, hang on. Add spotlight. There we go. You want
Yeah,
me to
so
get rid of
this
the
is-
other two, or?
Yeah, you can get rid of the other two, and we can just go
Okay.
to whoever's talking now, I guess.
Check.
Okay, so this is the sample holder that we have right now. You can see it's roughly like, it's here, I'll give you a metric. That's about 2 inches tall, 2 inches wide. That's the largest sample we can fit inside the chamber and still have room to move it up and down. As you can see, this is the last sample holder that got melted from the heat. This one hopefully can take the heat. Here is that's the little probe that's going to look at the camera, at the sample, and it's a fiberscope. And you can see actually, yeah, there you can see the sample in there. And it also moves left and right. So yeah, if anyone has any variations to this experiment, or thoughts of how to make it better, hit us up. If you have the metamaterials that you want to test, you have a piece that you think is from a crashed UFO, yeah, we'll stick it in here and we'll see what happens. We'll document it. This is probably
let's get Lou to bring that arts parts piece so we can shoot it with
Oh
some
yeah,
terahertz.
where's Lou Elizondo, dude? We'll give you all expenses paid. Come down here, Lou. We'll get this going. Here's the cover for it. So in between sample swaps, we can just slap
Mark,
that on there.
I posted a couple links for you on the chat for information on dynamic relaxation times. And it looks like most of the information is related to polymers or plastics. So, or amorphous solids. Just the FYI.
Okay, let me check that out. From Michael Boyd.
But do
Yeah,
it.
it does depend on temperature, which is an interesting thing, because that's another thing we're thinking of doing inside the chamber, is creating like a liquid nitrogen bath area to cool the sample down before we run it, to change the relaxation time. Possibly give us longer periods of time to be out of tune before the sample starts destroying the apparatus from heat. So yeah, that's one of our main concerns, is the heat damaging everything else. But I believe if you are in resonance, there shouldn't be any waste heat. Tim, are you there? Okay. Anyone else?
A quick comeback regarding relaxation times. I googled, and there are lots of articles about relaxation times of various materials. For example, niobium, various alloys, salts, quasi-crystals, nickel, copper. So one would have to start looking into these articles to see what materials were used and take the relaxation time from there.
Sure. If you can figure out, a salient theory why to try a certain material and what what parameters we should use on it, what gyromagnetic ratio, and yeah, if we can get it in the sample chamber, we'll run it and we'll see what's up and see what happens.
Yeah, so I would compare with what Alzofon did. So aluminum had some relaxation time, say 6 milliseconds, and they used some pulses of 8 milliseconds or 6 milliseconds, and then do something similar to the other materials depending on their relaxation times. I mean, use the relaxation time as a pulsing parameter.
Okay, that is one parameter. It's actually pretty easy to change it. You can, over here on the signal generator, this is the relaxation time controller. I think I'm doing this right. We actually have to hook this up to an oscilloscope to see exactly what's going out. But right now it's outputting, 9.25 gigahertz. This is the control you have over the frequency. So it's moving in tens of megahertz at a time. I don't know if that's enough fidelity in that control. At lower frequencies, I have a much higher fidelity signal generator that's digital. And this is the one we got for the cover the X band. So the pulses can either be input separately from a signal generator, or you can use the onboard pulse generator to create the pulses. And the only way we had to verify if pulses are actually happening is through our spectrum analyzer over here. And that you would see a spike turning on and off, but that only happens at the refresh rate, which is pretty slow. Right now it's 1/3 of a second. If you decrease the span, it gets down to 20 milliseconds is the tightest refresh rate. So you're not going to really be able to see 8 millisecond pulses accurately, or what's happening at a 20 millisecond refresh rate. It's refreshing slower than the pulse is happening. So yeah, probably hooking one of these up to an oscilloscope just to see what what it's outputting as pulse might help. There's also different versions of a we could do amplitude modulation on the signal. So we could put an AM signal on top of it. So if it's reaching resonance, what would that do? Sawtooth wave, square waves. There's lots of different options, but question is, what theory is there that tells us how to organize this mayhem?
So I would say that that's it. Alzofon's approach. So you have to know the EPR to know what frequency to use for your material. And then you have to know the relaxation time to know how you pulse those frequencies. And then just place it in a magnetic field and it should work.
Okay. Jeremy, how's it going online?
See, we have, I figured out the audio issue too, guys, because my audio wasn't working on my end. We have 81 people watching and 2 just dropped. See you later. Yes, they can hear me now. Everything's going good. I just had that screen up. There's my screen. Sorry about that. I'm using a virtual cam through OBS so that I can have different scenes. And I use this for my scene selection, a stream deck. So I'm trying to get a hang of all this technology over here. Get it all working. It's not always easy. You are watching live, yes. So I had some guys on Twitter that wanted to maybe jump on here, and this Generation Z podcast wanted to jump on with a bunch of our APEC guys and ask us some questions to do like kind of an impromptu interview. I don't know if they're here. I sent them a link.
I think we're in open discussion right now. So
Yeah, so we're in open discussion. I told them that if they joined during open discussion, they could host or start recording their own interview and come here and ask anyone who's on here any questions they want. So we'll see. Yeah, I don't know. He said the other guy couldn't make it because he's sick. But so maybe at the next one we can do this during the Q&A, because we're starting to get some more people from the alternative media interested in what we're doing over here. So it's good to get more people to come on and ask questions and see what's going on over here. I love the live chats too. We have a lot of people that just come on and watch this on YouTube and drop all kinds of great comments in the live chat. And thank you for being part of the community, guys. And come on in and sharing information. This is how we move forward with all this. Yeah, sorry I couldn't make it down. How was the Tesla conference too, by the way, Mark? Any footage or anything?
Yeah. Actually, I showed up there at around 10 or 11 in the morning, just to see what was going on. It was a couple dozen people there. And there was some pictures that were shared on the APEC 24/7 chat. That was live from the conference. We got a little bit of video as well. It was a smaller event. They were requiring masks, even though the Supreme Court just ruled that was unconstitutional. But I guess the hotels can do whatever they want. So they were requiring that you have the vaccination card. So you wouldn't have gotten in. I have another buddy that was there, Tom McNevin, who did most of the work on the CAD. Guys, give a round of applause to Tom McNevin. He came in today. Tesla conference. Oh, this is also Samuel Mason. Everyone, these are the local people who are also here for the for APEC's anniversary, right? And he just came down today to check out the lab and see what's up. And Tom helped out making the CAD, but he wasn't able to get in to the Tesla Tech place. So you were vaccinated, but you don't have your card, right?
Yeah, I showed them the text messages on my phone too of appointments and everything. And they're like, no, can't take it.
Yeah, it's like Nazi Germany.
I enjoyed a 4-hour walk around New York in 15-degree weather. And
like, what's next? Are they like gonna put us on the plantation, pick cotton?
Well, we're happy to spend the 10 conference days. Thanks.
Woo! Thank you. Oh, and this guy came in just in time to help us get. Yeah, we need Q-tips to clean some stuff up.
Oh, thank you, Samuel, and thank you, Todd. And what's the new guy's name?
Justice.
Justice.
I'm a volunteer some time here, so I'm gonna come in a better work attire, and then he'll be able to see my real skills. He thinks I'm like some
novice Poindexter guy. Can't do anything. 'Cause I'm dressed up.
Suit wearing jeans, dude. Yeah.
So now I gotta come in scrubs and really show him how to work the machine.
Yeah. So
All
that-
right.
he plans on getting a laser table, so we'll be able to
Yeah.
get some laser shit.
Yeah, I'm in the process of getting the Epilogue Fusion Pro.
Ooh.
Yeah.
How much does that run for?
It's like 32. 48 inch. It's like 32. It does the CO2 and the dual.
It's got the CO2 in it.
Yeah. it's
Oh,
just both.
nice.
Yeah, I'm getting the dual.
Sweet.
When we're talking about CO2 lasers, how many watts is that? What can it cut? But you can cut like sheet metal and stuff.
That would do
Nah,
no.
no, they
Now the way
not the warp engine. It's not gonna run
but
on that
the
kind of thing.
tabletop water jet I'm getting from
Oh.
Laser,
A water jet might work.
that one I'm getting the assembly. That one's like that. That's lit. That was only like 11,000. That one. Where's the water jet? It's gonna be.
So Justice over here is helping round out the lab with some more capabilities, and Samuel came by from the Tesla Foundation to check out what's going on and help out as well. In the end, it worked out pretty well. Jeremy, if you want to come down, I think next weekend is probably going to be better. We're going to have a photo shoot too, and just get professional pictures of everything, the setups and everyone. And
Yeah, I want to bring my camera too, because I have a good camera and that I need to put to better use and stuff.
right, the
So
still photo camera, you should bring that as well.
I also want to write some stuff because we need to, these 6-hour streams aren't for everyone. And a lot of people just want rapid fire bullet point, information. And I think we're going to benefit greatly if we put together some real short stuff, some real short content, like 5-10 minute video content, really well produced stuff. So I want to get working on that. Yeah, sorry I couldn't make it down this weekend, and as it turns out, it probably would have been a stupid idea anyway if I came down there.
Yeah, there's a storm coming into this nor'easter. You would have to drive back through it.
Oh, it's so cold. It's so cold here right now. Like, I don't know, my heat's working in my apartment and I'm still like, I have to wear a winter hat in here. It's warm in the bedrooms, but it's just cold here in my living room, where my setup is. So yeah, the crazy low temperatures. I feel like there's going to be some big snowstorms coming. I just feel like we're due for it. We haven't had like a real serious storm since like 78 up here in the Northeast. So I think we're due for it real soon. But
That would be nice. I got the snow tube ready. I got my skis. Did you ever use that GoPro camera to go skiing with?
not yet. I definitely want to get
So
some skiing.
bring
in,
it
though.
back here. I actually need it now because with these fiber scopes that I got, we got to hook a camera up to them. You can't just, there needs a camera there needs to be a camera at the end of it.
A fiber scope. What are you filming? Because the GoPros are good. They're great for like live action, like
No, you
outdoor
can't stick a
small.
you can't stick a GoPro inside of a microwave oven and have it give you live data, but through a fiber scope, which is this, you can. You see that image in the center? That's being fed from inside of the Faraday cage, that little black.
Is that a camera and that black wrapped in?
It's not a camera. It's a bunch of fiber optic cables organized in a fashion so that you can see it digitally analog.
Oh, so it's taking the
It's
actual
a digital
optical data.
analog. Yeah, it's a digital analog device. There's a bundle of fiber optic cables all grouped together that go down this thing. I'm not sure that we might have to get a specialized camera for it. I don't know if a GoPro would work, but yeah, there's a bundle of cables that go down to the end, and it gives you like a pixelated analog image.
How thin are the fibers in that
They're
bundle?
thinner than a human hair.
Oh, they must be, yeah, for to get that kind of resolution, because each one is
Not
like,
a lot of resolution, but it's enough resolution to see things moving around and get an idea what's going on.
what's the
it's not
bend
like-
radius on that cable?
It is in color. Yes, it is.
What's
You
that
got-
cable
What
called?
color?
What can I look that cable up?
It's called a fiber scope. A fiber scope.
Fiber
Is it the
scope?
same stuff that they use in laparoscopic surgeries, like that scope that they,
Yes, that
so
is
they can have
correct.
better resolution? Okay, all right.
Oh, there's a better image of it now. Look inside. Just look at my camera right now and you'll be able to see inside the fiber scope. Okay, you got it. Make a line for a
And
second.
what are we looking at?
You're looking inside of the Faraday cage.
Oh,
Well, is pointing
okay.
at where the camera is pointing.
Is that the copper thing?
Yeah. You see things moving around?
How
color.
much did that? How much did that go for? And what's the brand on that fiber scope?
To be honest, it's a very small market for this kind of stuff. This is from Shot Fiber Optics. It was actually broken when it arrived, but Professor Tom was able to fix it. There's actually not a very big market for these kind of things, and brand new, they're about $10,000, not for like 100. But I had to fix it. And there's another one coming in the mail that doesn't have the turning capability. Like this one can actually move at the end.
Yeah.
Also, it has a light. So this system over here, it pumps light through some of the fibers, and as you can see now that's all lit up. So it's
What's
pumping
the
light
zoom
into the
on it?
fiber.
What's the magnification on it?
There's not a lot of magnification in it. It's let me see, I'm gonna put this little plastic jar in there just so we can see if we can see it with the cover on. 'Cause now it's pumping light in from that light source. And with the cover closed, this is the actual setup. Yeah, we could barely see something there. Yeah, you can kind of see the sample or that little box that I put in it.
Yeah, like,
Yeah, that's the kind of view we can expect from inside of a microwave oven with a fiber scope. We have another scope coming in next week, so hopefully it has a better resolution and we could put a better camera on it set up so that we can see it more clearly.